Okay, hello Math 122 and welcome back to another video. So this is the beginning of chapter 5. We're starting in section 5.1, which is all about distance and accumulated change. So before we get into the topic for this video, I first want to kind of take a second to talk about an overview of calculus. Really when it comes down to it, calculus is all about two different operations. And the first operation is differentiation, which is something that you've now talked about for 3 chapters in a row. So it was introduced in chapter 2, you learned how to do some derivatives of functions in chapter 3, and then learned some application of derivatives in chapter 4. But the second operation, really fundamental to calculus, is called integration. And for the remainder of the class, we're going to be talking about integration and what it means and what we can do with it. So here's kind of the big question to be thinking about as we get going with integration in this video. If we have a function f of x, then we found out in the previous chapters that we can find the derivative of f of x, which we called f prime of x. But a natural question to ask is, well, if we start with the derivative instead, is it possible for us to go the other direction? So if we have our derivative already, f prime of x, is it possible for us to find that original function f of x? So this is a question to keep in mind as we start developing the integral, and we won't really get an answer to this question until the beginning of chapter 6, or maybe the end of chapter 5. But something to keep in the back of your mind. Okay, so a first motivating example for what we're going to talk about today is the following. So say we have a car and it's moving with a velocity that's given by the table that I have drawn here. So in the top row of this table we have time in seconds, and we're going from time equals 0 to time equals 10 with these 2-second intervals in between. So from 0 to 2, 2 to 4, 4 to 6, and so on, all the way up until we get to time equals 10. And then in the bottom half of the table here, we have the corresponding velocity of this car that we're talking about. So we're starting at 20 feet per second at time equals 0 and going all the way up, so the car is accelerating here to a velocity of 50 feet per second by the time we get to time equals 10 seconds. And the question we want to ask using this table is, can we determine how far the car has traveled? So this table is only giving us information about the velocity or the rate of change of the car that we're talking about. But it's interesting to ask, is the rate of change of the car sufficient to tell us exactly how much distance the car is actually covering here? And the answer is ultimately that we can't know exactly based on the information just given in the table here, but we can give a pretty good approximation. And to do so, we can assume that the velocity is going to remain constant over each of these 2-second intervals from 0 to 10 that are showing up inside of the table. So another piece of information we're going to need to do this calculation, remember that the distance an object travels is equal to its velocity, when the velocity is constant, times the amount of time that that object is traveling. So this is an equation that we're going to use over and over again here. And for this first approximation, let's assume that the velocity over each of these 2-second intervals is equal to the velocity on the left-hand side of each of the intervals. So what do I mean by that? I mean that if we're looking at the interval from 0 to 2, for example, this guy up here, then we're going to assume the car actually has a velocity of 20 feet per second over that whole interval. And if we're looking from 2 to 4, we're going to assume the car has a velocity of 30 feet per second, and so on, all the way over each of these 2-second intervals here. Okay, so let's see if we can approximate the distance that the car is traveling then. So to do this, let's start by the distance it travels from time equals 0 to time equals 2. So here, we're assuming that the velocity is 20 feet per second, because that's the velocity at t equals 0. So velocity equals 20. And now the distance traveled is equal to velocity times the time. So we say distance is equal to velocity, which is 20, times the time interval, which is 2, and we get a total of 40 feet. So this covers the first interval from time equals 0 to 2. But we can do this for all of the other intervals too. So how about from t equals 2 to t equals 4? So here, if we look up at the table, the velocity at time equals 2 is 30 feet per second. So now velocity is equal to 30, and distance is equal to 30 times 2 again. And this time we get 60 feet. So the car travels 60 feet in the time from t equals 2 to t equals 4. And we can keep doing this game over and over again. So t equals 4 to t equals 6 now. This time, the velocity is equal to 38. And the distance is going to be 38 times 2, which is 76 feet. Okay, now we can go from t equals 6 to t equals 8. And here, our velocity is going to be 44 feet per second, because that's the velocity at t equals 6. And again, we calculate the distance as 44 times 2 this time. And we get 88 feet. And then finally, the last interval, we can go from t equals 8 to t equals 10. And this time, the velocity is going to be equal to 48, because that's the velocity at t equals 8. And the corresponding distance is 48 times 2, which will be 96 feet. So now we calculated the distance that the car traveled, assuming that the velocity is constant, and using the velocity on the left-hand side of each of these 2-second intervals here. And we found the distance over each of these intervals. So to find the total distance that the car travels, for our approximation anyways, we're going to take each of these distances that we just found and add them together. So 40 plus 60 plus 76 plus 88 plus 96. And if we add these up, put them in the calculator, we get 360 feet. So this is an approximation for how far this car has traveled using the table here. Okay, so in this approximation we just did, again, we're using the velocity that's on the left-hand side of each of the intervals inside of the table, but maybe we should assume that the velocity is constant and that is equal to the velocity on the right-hand side of each of these intervals. So from 0 to 2, the velocity we would assume is 30 instead. And from 2 to 4, we would assume the velocity is 38. From 4 to 6, we assume it's 44, and so on. So we can use the velocity on the right-hand side of each of these intervals as well, and we get a different approximation. So let's do that. So from t equals 0 to t equals 2, this time the velocity is not going to be 20, the velocity is going to be 30, because we're using the velocity on the right-hand side of each of the intervals. So we get 30, and then the distance is equal to 30 times 2, which is 60 feet. Okay, we can do this again from t equals 2 to t equals 4. This time the velocity is equal to 38, I believe, because again we're using the right-hand side of the interval now. So the distance is equal to 38 times 2, which is 76 feet. We can go from t equals 4 to t equals 6. This time the velocity is equal to 44. And the distance is equal to 44 times 2, which is 88 feet. So if you want to go back and check these velocities, you can just pause the video or go back a few minutes in the video and look at the table and copy it down. Okay, from t equals 6 to t equals 8, the velocity is equal to 48. And so the distance is 48 times 2, which is 96 feet. And finally, from t equals 8 to t equals 10, the velocity is equal to 50. And so the distance is equal to 50 times 2, which is 100 feet. So this is the distance traveled over each of these small intervals, and to get the total distance traveled, we're going to add them all together. And you can trust me that when you add them all together, you end up with 420 feet. So notice that this approximation we found in the second case is different than the one we found in the first case. When we assume that the velocity was constant and equal to the right-hand side of each interval, we get a different approximation. And it's important to note that neither of these estimates we have, either 360 feet or 420 feet, are necessarily the right answer. They're both just different approximations that we can do. And on top of that, we could take both of these approximations and even average them to get another approximation instead, and we would get 390 feet. And this approximation of 390 feet is probably a bit better than either 360 or 420, but not necessarily. So here are a few different ways that we can approximate the total distance that the car travels. So in the previous example, the first estimate that we calculated is called the lower estimate because our approximation is smaller than the actual distance that the car traveled, and the second estimate is called the upper estimate because our approximation was bigger than the actual distance that the car traveled. So we can also use the data points from the table to plot a graph and then draw a smooth curve through those points. So I took the liberty of plotting the points already, but you can double check that these are correct if you want to. And I can draw a smooth curve through these points. And I want to show that the lower estimate and the upper estimate have a graphical interpretation using this picture that I have. So for the lower estimate, we're assuming that the velocity is constant, and we're using the velocity on the left-hand side of each of the intervals here. So I'm going to draw rectangles where I start at the dot on the left-hand side of each interval to give me the height of the rectangle. So I can draw them like this. And the lower estimate that we calculated is the area of these green rectangles that I just drew. And to represent the upper estimate, I'm also going to draw rectangles, but this time the height of each rectangle is going to be determined by the dot on the right-hand side of each of the intervals. So now I get these purple rectangles that look something like this. Okay, and the upper estimate is the area of the purple rectangles. So to get the lower estimate, I would take the area of each green rectangle and add it together, and to get the upper estimate, I take the area of each purple rectangle and I add it together. An important thing to note here is that the purple rectangles, if you look at the area that they enclose, it's going to be bigger than the area under the blue curve. And the green rectangles, if you look at the area they enclose, it's going to be smaller than the area that's under the blue curve. So this is an idea that's going to come up a little bit later. In the next section, I want to talk about ways that we can get better estimates for the distance that the car travels. So first off, here's a really important piece of information that you should write down. If we have a velocity function v of t, like we did in our previous example, and if v of t is always positive, then the total distance traveled is the area under the velocity curve. So here are some examples. In each of these examples that I have drawn here, the velocity curve, v of t, is going to be the blue curve. And in this first example, we can ask how close is our approximation to the true area under the curve after we've drawn these rectangles. So remember that these rectangles represent a lower or an upper estimate of the area under this curve here. And in the first example, when we're only using 4 different rectangles, notice that I have a bunch of area underneath the velocity curve that isn't being accounted for by any of my purple rectangles that give me my approximation. So in this case, maybe we would say the approximation is just okay. It's not bad, it's still relatively close, but we're missing out on a bunch of the area underneath this blue curve. In the next example, we have the same velocity curve, but this time we're using a bunch of different rectangles. I don't even know how many it is, maybe 15 or something. And this time, if we look at all the area that's not being accounted for, notice that we just have a bunch of really small triangles at the top of each of the rectangles here. So in this case, we use smaller intervals to approximate and more rectangles. This approximation is much better than the previous one. So as we use smaller intervals and we use more and more rectangles to approximate the area under the curve, our approximation is going to get better and better. And the actual distance traveled by the car is the exact area underneath this velocity curve. And at this point, I should probably stop saying car, because this holds for the velocity of any object. It doesn't have to be a car. Okay, so here's the key idea of these different examples. When we use more rectangles, which is the same as using smaller intervals, our approximation of the actual area, the area underneath the velocity curve, gets better and better. And a natural question for us to ask is, well, what happens if we use infinitely many rectangles? So in this second picture, I used a bunch of rectangles, but what if we used infinitely many instead? How good would the approximation be? And really, this green question right here leads to the definition of the integral that we'll get to in just a couple of sections. So far, we've only been talking about the relationship between velocity and distance traveled, but the idea that we've been bringing up is actually much more general. So here's another important fact that you should know. This is generalizing from the box that we had about velocity. If f of t is a function that gives the rate of change of any quantity for some time t, then the total change in the quantity from time equals a to time equals b, so over some interval of time, is the area under the curve of f of t from t equals a to t equals b. So this is really the same statement that we had for velocity, but now we're generalizing to include the rate of change of any quantity, not just the rate of change in terms of velocity. Okay, so some pieces of notation. We use the notation delta t to denote the size of the subdivisions that we're going to use from t equals a to t equals b. So in the first example, we went from time equals 0 to 2 to 4. Delta t in that example was 2. And we use n to denote the number of subdivisions from t equals a to t equals b. So the smaller the delta t, and the larger the n, in other words, the smaller the width of the rectangles under the curve, and the larger the number of rectangles we use, the better our approximations are going to be when we do them. Okay, so here's an example using this idea. So t is the number of hours since the start of a 20-hour period in this example, and a bacteria population increases at a rate that's given by this function f of t, is equal to 3 plus 0.1 t squared, and the units are millions of bacteria per hour. So we want to make a lower estimate of the total change in the number of bacteria over this period using a delta t of 4 hours and then a delta t of 2 hours. So we're going to do the problem 2 different times using a different value for delta t, and this is really all coming from this box up here. Okay, so let me do the example for you, and we'll see how it looks. So we're starting with delta t equals 4 hours, and we're going from t equals 0 to t equals 20. Okay, so the length of the subintervals is 4. So that's exactly what it means for delta t to be 4 hours. It means that the length of the subintervals that we're using to divide the interval from 0 to 20, they're each going to be 4. And how many intervals does this give us? That's going to be n. Well, n is going to be equal to the total number of hours, which is 20, divided by the length of each of the subintervals that we're looking at. So we have 20 divided by 4 is going to give us 5 total intervals that we're looking at. And to get an underestimate, we use the rate at the left-hand side of each of these intervals. Okay, so we're going to make a table to see all of these data points. All right, so in the top of the table, we're going to have time in hours, and in the bottom of the table, we're going to have f of t. Okay, and we're going from time equals 0 to time equals 20, and we're breaking up into 5 different intervals of length 4. So we're starting at time equals 0, then we're going to go to time equals 4, and then 8, 12, 16, and 20. So the reason I know the value of the time in the top of this table here is because I'm starting with the assumption that I'm going to use a delta t of 4 hours. So I want the length of each of these intervals from 0 to 20 to be 4 hours. And if you take each of these times and you plug them into the function f of t, which I won't do here, you're going to get the values 3.0 for time equals 0, then a 4.6, and then a 9.4, then a 17.4, then a 28.6, and finally a 43.0. Okay, so I'll tell you how to get these. We're going to take each t value, and we're going to plug them in to the function that gives us the rate of change of the size of the bacteria population, so f of t. All right, so at this point, to find the total change, we assume f of t is the left-hand value of each of the intervals that are showing up inside of the table here. Okay, and now we just have to do a calculation. So the total change is going to be equal to the time from 0 to 4, so we get a 4, times the value of f of t at the left-hand side of that interval, we get a 3.0, plus 4, which again is the length of this interval from 4 to 8, times the value of f of t at the left-hand side of the intervals. We get a 4.6. And we continue this all the way across the table to the right. So we get a 4 times a 9.4, plus a 4 times a 17.4, plus a 4 times a 28.6. And now we're done, because 4 times 28.6 gave us this last interval here from 16 to 20. And now we plug this into a calculator, and you find that this is equal to 252.8. So we conclude that the total change is estimated at 252.8 millions of bacteria. So this is the general process that we're going to use to perform these approximations. And in this case, we're just given this information that delta t is supposed to be 4 hours when we approximate before we start the problem. Okay, so in the second part of the problem, let's see what the approximation looks like if we use a smaller delta t. So we're going to be looking over smaller intervals from time equals 0 to time equals 20 and see if our approximation is different. So in this case, the intervals have length 2. So that's exactly what it means for delta t to be 2 hours. And again, we're going to set up a table, and the top is going to be t in hours, and the bottom is going to be f of t. And this time the table is going to be bigger because we're subdividing the interval from 0 to 20 into intervals of length 2 as opposed to intervals of length 4. So we're going from 0 to 2 to 4 to 6 to 8 to 10 to 12 to 14 to 16 to 18 and finally to 20. So as delta t gets smaller, this calculation can get more and more tedious, but I think it's important to show the calculation so you get a good idea for how it works. Okay, and now we're going to fill in the bottom side of this table here by taking each of these times and plugging them into the function, and we get 3, 3.4, 4.6, 6.6, 9.4, 13.0, 17.4, 22.6, 28.6, 35.4, and 43.0. And just like we did in the previous case, now to get the total change, we're going to look at the change over each of these intervals of 2 hours here. So the total change is equal to 2 times 3, so that's the length of this time interval, times f of t on the left-hand side, plus 2 times 3.4, again, the length of this interval, times f of t on the left-hand side. And we keep doing this over and over again. And maybe I'll just put a dot, dot, dot. So you keep doing this all the way up until you get to 2 times 35.4. So we get over to this interval and use the left-hand side of that interval for f of t. And when I add all of these together, I end up getting a 288. So if you want to, you can again pause the video and just check my math here, make sure that it's correct. So we conclude that the total change is 288 million bacteria. So this would be our approximation when delta t is equal to 2. Okay, and an important thing to notice that the change in the value for delta t changes the approximation. So as delta t gets smaller, the approximation is going to get better. Another way to say that is as n gets larger, or the number of subintervals that we're using gets larger, the approximation is going to get better. So that's the important thing to note between these two different examples here. Maybe I'll square that too. Alright, so in this last part of the video, I want to talk about making these approximation sums that we seem to be using over and over again a little bit more formal. So we're going to end up defining left and right-hand sums, which we'll be using a bunch for the remainder of the class. So let's say that f of t is some function, and we're looking at the interval from t equals a to t equals b. To get these left and right-hand sums, we start by dividing this interval from a to b into n smaller subintervals. And the length of each of these subintervals is going to be equal to b minus a, which is the length of the entire interval, divided by n, the number of subintervals that we're breaking into. From there, we can let t naught, t1, dot, dot, dot through t sub n be the endpoints of each of these subdivisions that we're breaking into. And the corresponding picture would look like this. So we have our function f of t is the blue curve in the coordinate plane here. And then we're breaking up into n different intervals, subintervals, with t naught, t1 up through t sub n being each of the endpoints of these intervals. And the length of each of those intervals is going to be delta t. So once we have this picture, the left-hand sum is defined to be the value of f at t naught times the length of the subinterval plus the value of f at t1 times the length of the subinterval plus all the way up until we get to f of t sub n minus 1, so the second to the last endpoint here, times the length of the subinterval. So why is this called a left-hand sum? Because when we're calculating the value for f for each of these intervals here, we're using the value of f at the left-hand side of each of the subintervals. On the other hand, the right-hand sum is going to be defined similarly, but it's a little bit different, because this time we start at f of t sub 1, and we go up until f of t sub n. And the reason that happens is because now we're using the right-hand side of each interval to give us the value for f. But we're still doing the same fundamental process. We get the value for f at one of the endpoints of the interval, and then multiply by the length of that interval. And we do this for all of the different intervals and add them together to get either of these sums here. Okay, so both of these formulas look kind of strange when you just write them down as they are. It's more helpful to think about them as pictures, the right-hand sum and the left-hand sum. So here are the accompanying pictures of what's going on. So in this first picture, I have the left-hand sum. So we have our function, which is blue. That's going to be f of t. And I've broken this interval up into a bunch of smaller subintervals. I think 5. Yeah, 5 subintervals in this case. And we're going to draw rectangles, but to draw the rectangle, we determine the height of the rectangle by the left-hand point of each of the intervals here. And if we have this drawing, then the left-hand sum is just the calculation of the area of all of these different red rectangles added together. Okay, and for the right-hand sum, again we have f of t as the blue curve. We've broken it up into 5 different subintervals. This time we draw rectangles, but the height of each rectangle is determined by the value of the function on the right-hand side of each of the subintervals. And the right-hand sum gives the area of these rectangles that I have drawn here, the area of each one added together. That's equal to the right-hand sum. Ultimately, it's more helpful to remember these pictures than it is to remember the formula. If you can remember the pictures, then you can just derive the formula or think about it for a little bit to get the formula, as opposed to having to remember them. But I'll leave that up to you. If you want to memorize it or print it out or write it, you can do that. But ultimately, both of these things, the left and the right-hand sum, are going to be fundamental for us for the remainder of the class. Okay, and finally, let's just do an example of calculating these left and right-hand sums for an abstract function. So in this case, our function is going to be f of x equals x squared plus 3. And for the first question, we're going to find the left-hand sum with n equals 4. So we're breaking up into 4 subintervals over the interval from 0 to 8. So we're taking that interval from 0 to 8, breaking it up into 4 subintervals, and calculating a left-hand sum. All right, so n equals 4. So to find delta t, or the length of each of the subintervals, I'm going to take the length of the whole interval from 0 to 8, and divide by n. And this tells me that delta t is equal to 2. And from here, I can make a little table. So we're starting at x equals 0, and we're increasing by 2 until we get up to x equals 8. And now we're going to take each of those x values and evaluate them with the function f. So at 0, we get a 3. At 2, we get a 7. At 4, we get a 19. At 6, we get a 39. And at 8, we get a 67. All right, and to get the left-hand sum, we're going to take the value of f at the left-hand side of each of these subintervals. So f of 0 times the length of the interval plus f of 2 times the length of the interval plus f of 4 times 2 plus f of 6 times 2. So this is going to give us our left-hand sum. And if we put in the appropriate values, we get a 3 times 2 plus a 7 times 2 plus a 19 times 2 plus a 39 times 2. And if you plug this into a calculator, you should get 136. So this would be the value of the left-hand sum of this function f of x when n is equal to 4. Okay, we can do a similar calculation, but instead do the right-hand sum with n equals 4 as opposed to the left-hand sum. So again, n equals 4 means that we're going to break up that interval from 0 to 8 into 4 subintervals. So delta t is again going to be equal to 2. And we can use the same table that we had before of x and f of x. The difference is that this time, to calculate the right-hand sum, we're going to use the value of f on the right-hand side of each of the subintervals that we have here. So we're going to have f of 2 times 2, as opposed to f of 0 times 2, plus f of 4 times 2, plus f of 6 times 2, plus f of 8 times 2. And again, if you take each of these f of whatever number is inside of there, and you plug them into the function, and you add them together, you're going to end up with a 264 in this case. So the right-hand sum is 264, the left-hand sum is 136. So depending on if we do a left or right-hand sum, we get a different value, even though we're breaking up into the same number of subintervals. All right, so I know that this video is a little bit longer than the other videos, but I thought that I would make it a bit more comprehensive for those of you who want some more examples or detail. In future videos, feel free to skip through most of what I say or use the notes and just look at things that you find important when you're going through the homework. That's perfectly fine to me. But I will see you in the next video, section 5.2.